One of the things that we need to know is what we mean when we say standard position. So all standard position means is that the initial side of our angle, so basically where we start measuring, so this part right here is on the x-axis, on the positive part of the x-axis. And of course, we know that the terminal side, which is the other part of our angle, that this is going to point elsewhere. And technically, it could point in the same direction, and that's a special case that we'll consider later on. So this is an angle in standard position, and this is an angle that is not in standard position. Notice one of the differences also is that the vertex has to be on the origin if an angle is in standard position. Do you know what this angle is? How much is it? Well, this angle is 30 degrees. And we normally just say 30, but we want to clarify and say that this is actually positive 30 degrees. And we measure it by going in this direction. So we're moving in the counterclockwise direction when we measure positive angles. So what about if we move it further in the counterclockwise direction? So let's say we were to move the angle here, or the terminal side of the angle here. What would it be? So this would clearly be a positive 45 degrees. We could move it up some more in the counterclockwise direction. Now we're measuring a positive 60 degrees. We can continue. This is a positive 90 degrees, and so on. This is a positive 135 degrees, and we can keep going. So if we can measure positive angles, then we should be able to measure negative angles also. So let's go back to where we started. So this is where our terminal side was initially. But what if we went 30 degrees the other direction? So what if we went 30 degrees in the counterclockwise, rather in the clockwise direction? In the clockwise direction, 30 degrees would put us at a different location. So negative 30 degrees looks like this. So negative 30 degrees is equal to a positive 330 degrees. So let's look at what negative 60 degrees looks like. So negative 60 degrees would look like this. Negative 90 degrees would look like this. And we can keep going and continue with additional measurements. So hopefully you have the idea of how positive or negative angles look. So positive angles are measured in the counterclockwise direction, and negative angles are measured in the clockwise direction. One observation that we want to make is that 360 degrees brings us right back to where we started. So as an example, if I went from 0 360 degrees around, that would put me right back where I started. So if I'm already at 30 and I go 360 degrees around, then that's going to put me right back where I started. So what we just described were actually coterminal angles. Initially, when we looked at this, we were just looking at 30 degrees. But what we're saying is that if we go another 360 degrees, that we end up right back where we started. So in other words, 30 degrees is coterminal with 390 degrees. Even if we went 2 rotations, so now we're at 390. Let's go another 360. Now we're at 750. So if we go around here twice, we end up back where we started. Now we have what's basically described as a coterminal angle. So all coterminal angles are angles where the terminal side and the initial side are exactly the same. And we can get coterminal angles basically by adding or subtracting 360 degrees to the angle, or multiples of 360 degrees to the angle that we have. So, for example, if we were to go back the other direction by 360 degrees, we would have gone a negative 330 degrees. So in other words, 30 degrees is coterminal with negative 330 degrees. Also, if we went 2 rotations, we would end up essentially traveling a negative 690 degrees. So let's look at the math. Let's see exactly what this looks like. So what we're saying is that 30 degrees is coterminal with 390 degrees because we can add 360. In other words, we can go a full circle around of 30 to get 390. Also, we know that 30 degrees is coterminal with 750 degrees because if we went around 2 times, we would have gone around 720 degrees. So if we add 720 degrees, we'll get 750. So 30 degrees is coterminal with 750 degrees. We know that if we're uh, going the other direction, that's a negative direction. So as an example, 30 degrees is coterminal with negative 330 degrees because if we take away one rotation, if we take away 360 degrees, it's going to give us negative 330. So 30 degrees is coterminal with negative 330. Also, 30 degrees is coterminal with negative 690 degrees because again, if we go around 2 full rotations in the clockwise direction, that means that that's the negative direction. We're subtracting 720, which gives us negative 690. So 30 degrees is also coterminal with negative 690 degrees. And all coterminal means is that, again, when we go around, we end up right back where we were. Reference angles are the smallest angle between the terminal side and the x-axis. So let's say we take this angle, 130 degrees, and we need to find the reference angle. The reference angle would be the angle that's the smallest distance to the x-axis. So in this case, this is the smallest distance to the x-axis. So our reference angle here would be 50 degrees. We say 50 because there's a difference of 50 between 130 and 180. So our reference angle again here is 50 degrees. Try to see if you can come up with the reference angle for this particular angle. So here, this angle is a positive 220 degrees. Or if we want to think about it as a negative angle, it would be a negative 140 degrees. So what's our reference angle here? Our reference angle, again, is the shortest distance between our terminal side and the x-axis. So there's our reference angle. How much is the reference angle? Well, remember that we're at 220 right now, and that we're going the distance from 220 to 180, which is a distance of 40 degrees. So our reference angle here is 40 degrees. So what's our reference angle here? All right, this angle is either a positive 320 degrees or it's going to be a negative 40 degrees. So our reference angle, again, is the shortest distance to the x-axis. So that would be this distance here. Remember that we're looking at the difference of 360 and 320 to find our reference angle. So here our reference angle is 40 degrees. Quadrantal angles are another definition that we're going to need. Quadrantal angles are basically the angles formed by the axes. So right here we'll see that the green line is on 0 and the the red one is on 90. So our initial side is on 0 and our terminal side is on 90. So this is an example of a quadrantal angle because we're using the axes, the x or the y axis, to form the angle. So 90 is a quadrantal angle. 180 is also a quadrantal angle, as we're using the axes to form that particular angle measurement. Also, 270 is a quadrantal angle, and so is 0 or 360 degrees. Those are all quadrantal angles. Let's start summarizing what we know, and we're going to build up to a definition of radians and how we can apply everything to the unit circle. So by unit circle, we mean that we have a circle that has a radius of 1. So unit basically here is just referring to 1. So if our circle has a radius of 1, that means that this point here would be the point 1, 0. This point here would have to be the point 0, 1. This point would have to be the point -1, 0. And this point would have to be the point 0, -1. From the discussion that we just had about quadrantal angles, we know that the angle that would have been here would have been the angle 0 degrees, that 90 degrees would have gone up here at the top, that 180 degrees would have gone here on the side, and that 270 degrees would have gone here. So now we've just built a few relationships around points and angles to start building our unit circle. But we said that we are going to talk about something called radians. So what exactly are radians? Well, we want to make an observation first. We said that we're dealing with a unit circle. So basically the radius of that circle has to be 1. So how would we describe the distance around that circle? Well, we know that we would use the formula for circumference, and that circumference is equal to 2 times pi times the radius. But remember, we know what the radius is because we're dealing with a unit circle. The radius is 1. So in other words, the circumference of this circle is 2 times pi times 1. In other words, 2 pi. So the full distance around this circle is going to be 2 pi. We'll describe that as 2 pi radians. So when we go half the distance around the circle, so from here to here, we haven't gone a full 2 pi, we've only gone pi units. So we can say that 180 degrees really represents pi radians. If we go the full 360 degrees, so if we go the rest of the way, then again, we would have gone 360 degrees, which from our discussion just now is going to be 2 pi radians. So what about the other quadrantal angles? What would those be if we represented them with radians? Well, if we know that 180 degrees is equal to pi radians, and we needed to get 90 degrees, what do we need to do? Well, clearly we would need to divide what we had up here by 2 in order to figure out what 90 radians is. So basically 90 radians has to be pi over 2. 90 degrees has to be pi over 2 radians. Also, what about 270 degrees? Well, we would have to multiply 90 by 3 in order to make that happen. So 270 degrees is equal to 3 pi over 2 radians. So let's put everything that we know so far together about our unit circle. So what we know is that this section here of our unit circle can represent 0 degrees or 360 degrees if we go one full rotation and come back around to it. We know that the coordinate is 1, 0, and we know that 360 degrees represents 2 pi radians. We know that this section here represents 90 degrees. We know that its coordinate would be 0, 1, and we know that 90 degrees can be represented by pi over 2 radians. This particular point here is 180 degrees. We know that its point would be -1, 0, and that 180 degrees is represented by pi radians. This point is 270 degrees, and that it is the point 0, -1, and 270 degrees is 3 pi over 2 radians. So this is the basic format for our unit circle, and we're going to build on that later on. So how do we convert between degrees and radians? How do we go from degrees to radians? So we remember that we know what 90 degrees is, that 90 degrees is pi over 2 radians. So how can we get that? How can we develop a unified strategy to figure that out? Well, notice that first of all, that pi radians is 180 degrees. So if we divided everything by 180 degrees, that we're basically just saying 1. Or if we did it the other way, so if we had pi equals 180 and we decided to divide everything by pi this time, then we're saying that 180 over pi is basically 1, because 180 and pi are the same thing. If we divide by each other, if they divide by each other, they're just going to give us 1. Now think about what happens. If I take 90 and multiply it by 1, then it's still equal to 90. Or if I take 270 and I multiply it by 1, it's still 270. So maybe we can use these conversion factors to help us out. So let's say that we wanted to convert 90 degrees to radians. We could say 90 times one of these. Let's say we chose the one on the right. So we said, no, the left. So let's say we said pi over 180, and we know that this is basically 1, so it's still equal to 90. So think about what happens if you multiply by pi over 180. This factor and this factor, they have 90 in common. So 90 divided by 90 is 1, and 180 divided by 90 is 2. So we end up with pi over 2. So pi over 2 is the same as 90. So basically what we can do is we're going to multiply by this one whenever we want to change from degrees to radians. So logically then, we would use this conversion factor whenever we're going from radians to degrees. So as an example, 270, we want to convert that to radians. So we're going to multiply by pi over 180. We put the 270 over 1. 270 and 180 are both divisible by 90. If you divide 270 by 90, you get 3. If you divide 180 by 90, you get 2. You multiply straight across, you end up with 3 pi over 2. So 3 pi over 2 is the same as 270 degrees. So let's say that we did one that we already knew as well, 2 pi, or rather 360, and we want to convert it to radians. We can multiply that by pi over 180, put this over 1. These are both divisible by 180, so this will go 2 times, and this will go 1 time. We multiply it across, we end up with 2 pi over 1, which is just 2 pi. So if we're going from degrees to radians, multiply by pi over 180. If we're going from radians to degrees, then we have to multiply by our other conversion factor. So let's say that we had pi over 6, and we wanted to convert that to degrees. Well, first of all, one way to do it is to know what pi is equal to. Remember that pi is the same as 180 degrees. So technically, we could just say that this is just 180 degrees divided by 6, which is 30 degrees. But let's say that we wanted another strategy. What we could also do is we could say if we had pi over 6, we could multiply by a conversion factor, which is 180 over pi. Notice that the pi's are going to eliminate. Both 6 and 180 are divisible by 6, so 6 divided by 6 is 1, and 180 divided by 6 is 30. And if we multiply across, then this is just going to be 30 over 1, which is just 30. So let's try another one. Let's say we had pi over 4, and we wanted to convert that. So what we would do is we could say that this is basically 180 divided by 4, and if you divide that yourself, you're going to get 45. But a second way that we could do it is we could say, I'm going to multiply by my conversion factor. So pi over 4 times 180 over pi. The pi's are going to eliminate. Both 4 and 180 are divisible by 4. 4 divided by 4 is 1, and 180 divided by 4 is 45. And we multiply across, it's 45 over 1, which is just 45. So either way, you'll get the correct answer.